Kirchhoff's voltage law and Kirchhoff's current law, along with Ohm's law, provides a set of powerful tools for solving most of the circuits. And there are two Kirchhoff's laws. One is Kirchhoff's current law, which states that the algebraic sum of the currents entering a node or a closed boundary is 0. And here if you see this figure, a node is actually a meeting point of more than one circuit elements. At least two elements will be meeting at that point, or at a common node, or a common point, that is node that we have already seen. And if you consider this node in this example, here you can see that. And when we express Kirchhoff's law as sigma n equal to 1 to n in equal to 0, here you can see that mathematically this represents the algebraic sum of the currents meeting at a node is equal to 0. So here actually algebraic sum means you have to assign a positive or negative sign depending upon whether the current is flowing into a particular node or flowing out of the node. And you can see that in this example, if you are taking, say for example, I1 is marked as current coming into the node, and say I5, say I2, this I5 and I2 are flowing out of the nodes. So if you are assigning positive sign for the currents coming into the node or entering into the node, if you are taking it as positive, you have to consider the currents leaving the node as negative, or vice versa. For example, you can take the currents entering the node as negative and current flowing out of the node as positive. It's up to you. But algebraically, if you add these currents, it will be equal to 0. So in this case, if you are assuming currents entering into the node or current flowing into the node is positive and the current flowing out of the node as negative, this equation, you can formulate this equation here. Here you can see that I1 is the current flowing into the node. Similar is the case with I4. So I1 is positive, so you can assign a positive sign here, and this will also be positive, and in this case it will be negative with our sign convention. That means we are taking current flowing into the node as positive and current flowing out of the node as negative. So I1 is positive, I4 is positive, I3 is also, this is also positive, but I2 and I5 are negative. So if you add these currents, that means algebraically add means adding the currents after assigning proper sign, it will be equal to 0. So in this case, you can see that I1 plus minus I2, because minus I2 is flowing out of the node according to our sign convention. So I1 minus I2 plus I3. Here you can see that I3 is coming or flowing into the node. So it's taken as positive. And I4, here you can see that I4 is also coming into the node or flowing into the node. So we are taking it as positive, and I5 is negative there. So minus I5. That will be equal to 0 if you add these currents together. That is I1 plus I3 plus I4 minus I2 minus I5 equal to 0. So if you rearrange these terms, you get this equation, I1 plus I3 plus I4 equal to I2 plus I5. So sum of the currents entering a node is equal to the sum of the current leaving the node. That you can get from here, because I1 plus I3 plus I4, you can see that the total currents flowing into the node or entering into the node is equal to the sum of the currents leaving the node. That is the gist of the Kirchhoff's current law. So if you know, so you can get a set of equations if you apply Kirchhoff's current law at a particular node, and depending upon the circuit configuration, you can formulate enough number of equations and try to solve the circuit. Kirchhoff's current law can also be applied to a closed boundary. In that case, you have to consider the currents entering the boundary as positive and the current leaving the boundary as negative, or vice versa. So after assigning proper signs to the currents entering or leaving, if you algebraically sum up the currents, you will be getting it as 0. That is actually a generalized Kirchhoff's current law. And you can consider a node in a circuit as a boundary which is or a closed surface shrunk to a point. That is, this is actually the generalization of the Kirchhoff's current law. And if you consider the Kirchhoff's voltage law, first is the Kirchhoff's current law, and second one is the Kirchhoff's voltage law. Kirchhoff's voltage law states that the algebraic sum of all voltages around a closed path for loop is 0. That means if you consider, say, for example, this closed loop, if you start from this point, for example, if you mark the nodes as, say, point 1, say 2, 3, 4, 5, and finally, so if you start from this node, for example, and if you say from 1 to 2, 3, 4, 5, 1, so that is a closed loop. 1, 2, 3, 4, 5, finally you will be reaching the point or node 1 itself. So it's a closed loop, and you can see that you have traversed a number of elements, circuit elements, but only once. If you algebraically sum up the voltages, it will be 0. So in that case, algebraic sum means if you are meeting a rising potential, if you consider it as positive, and if you meet a drop in potential, it has to be considered as negative, or vice versa. That means if you meet a rising potential and if you are considering it as negative, in that case, if you are meeting a drop in potential, you have to consider it as positive. So if you come into this loop 1, 2, 3, 4, 5, if you start from the node 1, and if we are assigning positive sign to a rising potential, so here you can see that from when you travel from node 1 to 2, you are meeting a rising potential. Here you can see that this is an independent voltage source, and you are meeting in this directional travel. That means this is the loop we are considering. Actually, you can go this way also. So in this way, you can see that if you start from node 1 to 2, you are meeting a rising potential, and if you consider it as positive, you will get a equation, say V1 here. Similarly, actually you are meeting a drop in potential. So if you consider a rising potential as positive, the drop in potential should be taken as negative. So in that case, it will be minus V. And here also, if you travel from say point 3 to node 3 to node 4, you are actually meeting a drop in potential. So it will be minus V3. Now you have reached here, and when you travel from node 4 to node 5, you are meeting a rising potential. So it has to be considered as positive. So you get V4. And if you move from node 5 to node 1 in order to close the loop, you can see that here you are meeting a drop in potential, and you have to consider that as negative. So you have minus V5. That will be equal to 0 according to Kirchhoff's voltage law equation or Kirchhoff's voltage law. Now if you so we have obtained a equation V1 minus V2 minus V3 plus V4 minus V5 equal to 0. Now if you rearrange this, you get here V1 plus V4 will be equal to V2 plus V3 plus V5. This is the equation you are getting from this. Same equation can be obtained if you assign Kirchhoff's, or if you assign a rising potential as negative and a drop in potential as positive. That is, this is the equation you will get. So here you can see that if you travel from this point, say if you travel from this point or start from the point 1 and reach node 2, you are meeting a drop in rising potential. So if you are assigning it as negative, you get the term minus V1. Similarly, you are meeting a drop in potential, and with this sign convention, it is positive. Similar is the case with here, because you are meeting a drop in potential and you are considering it as positive. So V3, and here you can see that you are meeting a rising potential and you are considering it as negative. So you get minus V4, and at this point you are meeting a drop in potential. So it is to be considered as positive. So you get this equation minus V1 plus V2 plus V3 minus V4 plus V5 equal to 0. and you will end up with the same equation. And similar is the case if you consider a loop like this. Same equation you have to get. Here you can see that if you start from this point, say node 1, you are traveling in this direction and with a sign convention. For example, we consider the sign convention of if you are meeting a rise in potential, you consider it as positive, and if you are meeting a drop in potential, that means if you are traveling from a positive polarity to negative polarity, you consider it as a drop in potential, and that drop in potential or that voltage is considered as negative. So if you follow this sign convention, let us see what equation we will get. So if you start from node 1 and when you reach node 5, actually you are meeting a rise in potential and we are considering it as positive. So the term will be say V5 plus V5, and when you travel from node 5 to node 4, you are meeting a drop in potential. That means it has a negative sign, so you get minus V4. And from node 4 to 3, you are meeting a rise in potential, so it will be positive here. And from node 3 to 2, you are meeting a rise in potential because you are moving from a negative polarity to positive polarity. So you have a term plus V2 here. And from node 2 to node 1, you are meeting a drop in potential. So you have a term minus V1. And according to Kirchhoff's voltage law, this will be equal to 0. Algebraic sum of the voltages around a closed loop is equal to 0. Now the same equation you can obtain from here because you get V5 as positive and V5, V3 and V2 as positive. That means V2 plus V3 plus V5. That will be equal to V4 plus V1. That means whatever sign convention you follow, either you are or whether you are considering a rise in potential as positive and a drop in potential as negative or vice versa. And this is the application of the Kirchhoff's voltage law. So in a nutshell, Kirchhoff's voltage law is sum of the voltage drop is equal to sum of voltage rises. Now let us see how this Kirchhoff's voltage law and current law along with the Ohm's law can be used for solving a circuit. For solving a circuit means you have to find the current through any element and the voltage across the any element. So here you can see that you have 3 resistances connected to a constant voltage source. And if you consider this numerical problem, the question or the problem is to find currents and voltages in the circuit. That is actually the solution of the network, and its solution can be obtained using Kirchhoff's current law and voltage law along with the Ohm's law. So a solution will be like this. Here you can see that if a current I1 is flowing through an 8 ohm resistance and with these directions of current, the polarities of the drop across this resistance. Here you can see that I1 is flowing through this resistance 8 ohm, I3 is flowing through this 6 ohm resistance, and I2 is flowing through this 3 ohm resistance. So because of the flow of these currents, the voltage drop across the resistances are shown with the proper polarity. That means here you can see that current is flowing in this direction, so the voltage drop will have positive polarity here and negative polarity. Similarly, if this current I2 is flowing in this direction, the voltage drop across the resistor, the terminals of the resistor will have these polarities. Positive will be here and negative will be there. Similarly, if a current is flowing like this through this resistance, current is flowing in this direction, that means current will be flowing with positive polarity to the negative polarity. So the drop across the resistance will have these polarities. Now if you apply Ohm's law, here you can see that the drop across a resistance is given by I into R, the magnitude of the current I and the resistance. So here you can see that V1 is the drop across the 8 ohm resistor. So you get an equation V1 is equal to 8I1 because V1 is the drop across the 8 ohm resistor. So V1 is equal to 8I1. Similarly, here I2 is flowing through this 3 ohm resistor and the voltage across the resistor is V2. So V2 is equal to 3I2. Similarly, the drop across the 6 ohm resistor is V3 and it is given by I3 into 6 ohm. So you get another equation. V3 is equal to 6I3. Now we have seen that if you apply Kirchhoff's current law, applying Kirchhoff's current law at node A. This is the node A. Node is the meeting point of more than one circuit elements. Here you can see that at this node A, 3 elements are meeting. Now if you apply Kirchhoff's current law and we are assigning positive sign to the current coming into the node and negative sign for the currents flowing out of the node. So here you can see that I1 is flowing into the node, so it can be taken as positive, and the currents I3 and I2 are flowing out of the node, so they are taken as negative. Now if you apply Kirchhoff's current law at node A, Kirchhoff's current law states that the algebraic sum of the currents meeting at a node is equal to 0. So algebraically, if we are assigning positive sign to I1 and negative sign to I3 and I2, it's because I1 is flowing into the node and I3 and I2 are flowing out of the node. So if you apply Kirchhoff's current law, we get this equation. I1, because I1 is positive, plus minus I3, because I3 is flowing out of the node, plus minus I2 equal to 0. This is the result of application of Kirchhoff's current law at node A. So from this equation is I1 minus say I3 minus I2 equal to 0. So you name it as equation 1. And now if you apply Kirchhoff's voltage law to this law, actually we have 3 unknown values, I1, I2 and I3. So if you have to get a solution for a circuit, you have to evaluate I1, I2 and I3. That means 3 variables are there. So at least you have to have 3 independent equations. Then you can solve those 3 independent simultaneous equations to get a unique solution. So one equation is I1 minus I3 minus I2 equal to 0. The other 2 equations can be obtained by applying Kirchhoff's voltage law to this loop. So this can be considered as loop 1 and this is loop 2. Now if you apply Kirchhoff's voltage law to loop 1, that means applying Kirchhoff's voltage law to loop 1. So by applying Kirchhoff's voltage law to loop 1, say if you start from this point, you have to consider a closed loop. That means if you start from a particular point in the loop, you have to traverse through the elements and reach at the same point. And in this case, if you apply Kirchhoff's voltage law to loop 1, if you start from this point, when you reach up to this point, you can see that you are meeting a rising potential. So according to the general convention, the rising potential can be considered as positive. So we are meeting a rising potential with strength 30 volt. So it will be plus 30. So applying Kirchhoff's voltage law, you have a plus 30 there. Now if you are traveling in this direction, you have a drop. You are meeting a drop in potential because you are moving from a positive polarity to a negative polarity. And this V1 is the voltage across 8 ohm resistor. It's marked like that. So when you travel from this point to this point or from this node to this node, in traversing the loop 1, we have started from this point, we have reached up to here and we got this term. And from this point to this point, you are meeting a drop in potential. So according to the convention, it can be considered as a drop in potential. So we are assigning a negative sign to that. So you get minus V1. Now you have reached at this point, and from node A to this node, you are meeting a drop in potential whose magnitude is equal to V2. So when you meet a drop in potential, you are actually meeting a negative voltage, so it will be minus V2. Now you have reached at this point, and this was the point from we have started, and these 2 points are same nodes. There is no voltage drop across this. So according to Kirchhoff's voltage law equation, this will be equal to 0. So you get this equation, which can be rewritten as 30 is equal to this minus V1 and minus V2 goes on to the other side. So you have V1 plus V2. So it can be assigned as equation 2. Similarly, now if you apply Kirchhoff's voltage law to loop 2, applying Kirchhoff's voltage law to loop 2. So this is the loop, complete loop. If you start from this point up to the node A, then here, then up to here, then up to here. That means you will be traversing a complete closed loop. So if you start from this point, according to the marked loop, so if you start from this point and when you reach node A, you can see that you are meeting a rise in potential. That means you have a term plus V2. You have to remember that here you are meeting a rise in potential when you travel in this direction. You are moving from a negative polarity to a positive polarity. So you have a term plus V2 here. Now we have reached here, and when you move from node A to this node, you are meeting a drop in potential because you are moving from a positive polarity to a negative polarity. So according to this sign convention, with this direction of movement, you can see that you are meeting a drop in potential. So you have a term minus V3, and you have reached at this point. That means you have completed the loop. So according to KVL, it will be equal to 0. So you get another equation as V2 is equal to V3, and you can name it as equation 3. Now you have 3, either you can substitute because you have V1, V2 and V3 in terms of I1, I2 and I3. Either you have to solve for I1, I2 and I3, then from these equations you can get V1, V2 and V3. So this is first equation in terms of I1, I2 and I3, and in this case you have another equation 30 is equal to V1 plus V2, but you can substitute V1 and V2 from here. So you get the equation. This equation can be rewritten as 30 is equal to, you have V1 as 8I1 and V2 as 3I2. So 8I1 plus 3I2. 8I1 plus 3I2. That is V1 plus V2 is equal to 30. Similarly, here you have V2 is equal to V3. That means V2 is equal to V3 means it is 3I2 equal to 6I3. So this is the third equation. 3I2 is equal to 6I3. So now you have to solve these three simultaneous equations to get a unique solution for I1, I2 and I3. Once you get I1, I2 and I3, you can calculate V1, V2 and V3, and that will give you the solution for this network. This equation 3 can be rewritten as 3I2 minus 6I3 equal to 0. The above three equations can be rearranged like this. Now in matrix form, in order to solve these three simultaneous equations, either you can solve it by substitution method. You can substitute, say here you can substitute 3I2 is equal to 6I3. From here you can evaluate I2 and it can be substituted here in terms of I3, and you can solve the resulting simultaneous equations, or by applying Cramer's rule you can easily solve these three simultaneous equations. According to Cramer's rule, if you rearrange this in the matrix form, these equations can be written in matrix form as, say, I1, I2, I3. These are the variables, and in matrix form you have 0, 30, 0. These are the and here you have the matrix 1 minus 1 minus 1, and here you have 8i1, so you have 8 here, 3i2, so plus 3 here, and 0i3 there, so you can put 0 here, and here you have 0i1, so you have 0, here you have 3, here you have minus 6. So this is the matrix equation. So according to Cramer's rule, if you find the determinant of this matrix, say let it be delta. Determinant delta is determinant of this coefficient matrix 1 minus 1 minus 1, 8, 3, 0, 0, 3, minus 6. This is the determinant of this matrix. So if you find the determinant of this, you get it as a, the expansion, or how to find the determinants. So it will be 1 into 3 minus 6. 1 into 3 into minus 6. So you have minus 18 minus 1 into, you have 8 into minus 6 minus 48 minus 0 plus minus 1 into 8 into 3, 24. That will be equal to minus 18 minus 48 minus 24 equal to minus 90. Now you have to find delta 1. Delta 1 is obtained by replacing the first column with this matrix, this column matrix. So delta 1 will be, determinant of this column will be replaced by this matrix. So you have 0, 30, 0, and the other column will be the same, minus 1, 3, 3, minus 1, 0, minus 6. We have to find this determinant. This will be equal to 0 into this minus 1 into minus 180. So minus 180 plus minus 1 into 90. So it is minus 270. This will be equal to minus 270. Similarly, you can find delta 2 and delta 3. Delta 2 is obtained by replacing the second column with this column matrix, and delta 3 is obtained by replacing the third column with this matrix. Now delta 2 is the determinant 180, 0, 30, 0, minus 1, 0, minus 6. The second column is replaced by the column matrix, and that will be equal to 1 into minus 180 minus 0 minus 0 into 48 minus 1 into 0. So it's equal to minus 180. Similarly, delta 3. Delta 3 is the determinant 180 minus 133 minus 133, and third column is replaced by the column matrix 0, 30, 0. This is equal to 1 into 3 into 0 minus 90, 0 minus 90 minus 1 into 0 minus 0, so that is 0 minus 0 into something, that will be equal to minus 90. So we have delta is equal to minus 90, delta 1 is equal to minus 270, delta 2 is equal to minus 180, delta 3 is equal to minus 90. And according to Cramer's rule, I1 is equal to delta 1 by delta, that is equal to minus 270 divided by minus 90 equal to 3 ampere. and I2 is equal to delta 2 by delta, that is equal to minus 180 divided by minus 90, that is equal to 2 ampere, and I3 is equal to delta 3 by delta, that is minus 90 divided by minus 90, that is equal to 1 ampere. So we get the solution. I1 is equal to, so now we have solved the three simultaneous equations with three unknowns, and we have these results. I1 is equal to 3 ampere, so I1 is equal to 3 ampere, I2 is equal to 2 ampere, I2 is flowing through this, so it is 2 ampere, and I3 is equal to 1 ampere. So once you get the current here, voltage across the 8 ohm resistor will be given by 8I1. So V1 will be equal to 24 volts. Similarly, V2 is equal to the product of this resistance and the current flowing through that. So it will be equal to 6 volts here. And the voltage across the 6 ohm resistor, V3 will be product of this resistance value and current flowing through that. It will be equal to 6 volt. And it is from the circuit itself, it is clear that V2 will be equal to V3, because this V2 and V3 are the potential difference between these 2 points. So this point, the potential difference between this point and this point, here it is 6 volt. The same voltage is here because these two are parallelly connected resistors. So you get V1 is equal to 24 volt, V2 is equal to 6 volt, and V3 is equal to 6 volt. And that gives the solution of the network by applying Kirchhoff's voltage law and current law along with the Ohm's law.